Okay. Well, did I stop working already? All right. Talk a little bit about resonant or tuned circuits because it involves inductors and capacitors, which are the components. Two of them we learned about last week. We'll throw some new terms. We had only talked about resistance, which was the opposition to current flow, regardless of AC or DC. It's not frequency dependent. But we also have a term we call impedance, and we use a capital Z to represent impedance, where we use a capital R for resistance. And impedance is the opposition to alternating current flow. We still measure it in ohms, but it's a frequency dependent opposition. And the formula for impedance, show there, where it's equal to the actual resistance plus the reactance of the inductive and capacitive components. So they are say opposite polarity, so they can cancel one another out. In fact, that's what resonance is. When the inductive reactance and the capacitive reactance are equal, then all you have left is the pure resistance. If they're at a frequency where they're not equal, then you're going to have some vector value of R plus J X, some value in ohms. And we'll not talk about vectors yet. The next one is reactance, which we represent as a capital X. And we have an inductive reactance, which is usually represented by an X of L, which is 2 times pi times the frequency times the inductance in henries. And if you multiply that out for a given frequency, you'll find out what the reactance is in ohms. And we normally represent inductive reactance as a positive value. So if you plot it on a Cartesian coordinates, you'll plot resistance on the horizontal axis, and you'll plot inductive reactance on the positive going horizontal axis. We have capacitive reactance, which we usually represent as X sub C, and that's equal to 1 divided by 2 times pi times the frequency times the capacitance. We have so that when we have a circuit which composed of inductors and capacitors, either in series or parallel, that circuit will be resonant when the inductive and capacitive reactances are equal. And if you do the math and you set 2 pi FL equal to 1 over 2 pi FC, and you solve it for frequency, you'll find that it's equal to 1 over 2 times pi times the square root of the product of inductance and capacitance. And right now you don't have to remember all those formulas, but you will at some point. This is just a animation showing in a resonant circuit, what's happening is you're storing energy in the magnetic field of the inductor up until the point where the current stops and that field starts to collapse. That energy is then transferred to the capacitor, where it's stored in the electrostatic field, and the amount of energy is equal. So if there's no loss in the system, that would just continue to resonate, and they would just go back and forth. Now, because in the real world there's some loss, it's going to eventually die out. So to keep a circuit resonant, you normally have to feed it a little bit of energy to keep it going. And that's how an oscillator works. It will feedback some of the signal from that tank circuit or resonant circuit and feed it back to it just enough to keep it oscillating. When we put the inductors and capacitors in series, we call that a series resonant circuit. If we put them in parallel, which is what you see there in the animation, it's a parallel resonant circuit. They behave different. If they're in series, it appears to be a very, very low impedance at the resonant frequency. When they're in parallel, it looks like a very high impedance at the resonant frequency. So in other words, in series, it passes current at the resonant frequency. At parallel, it basically blocks current flow at resonant frequency. And like I said before, the circuit composed of inductor and capacitor is resonant when the reactances are equal between the capacitance and the inductance. And that's the formula there again, are the two formulas, and they're equal. This plot is kind of showing versus frequency how the impedance changes. So you see on the inductor at zero frequency or DC, it has basically no resistance or reactance. As frequency goes up, the reactance of the inductor increases. Capacitor is just the opposite. At 0 hertz, it's going to have a very high impedance because it's not going to pass a DC current. As the frequency goes up, the impedance of the capacitor, or the reactance of the capacitor, decreases. At the point there on the diagram where they cross is the resonant frequency. So they cancel out, and all you have is that resistance line, the red one, in the circuit. Down at the bottom, we show on the left side, a parallel resonant circuit and a series resonant circuit on the right. And they both have some resistance, so it's an RLC circuit. This is what I mentioned before. You have minimum impedance at the resonant frequency for series and maximum impedance at the resonant frequency for parallel. Those are the two main things you need to remember out of this. There's just some plots showing how the impedance changes with frequency for a series circuit, and how the current through that circuit changes with frequency. So you can see the current increases to a maximum value at the resonant frequency. you have kind of just the opposite charts for a parallel circuit, where the impedance goes up at the resonant frequency and the current goes down to a minimum at the resonant frequency. So which of the following is a resonant or tuned circuit?
A.
Yes. It will be, regardless of the value of the inductors and capacitors, it will be resonant at some frequency. Which of the following is combined with an inductor to make a resonant circuit?
E. Capacitor.
Okay, switches. We talked about those before, and they're used to open and close circuits. In the case of this one in the diagram, which is a single pole double throw, it can connect, in this case, the battery to one of two circuits, either to the regular light bulb or to the LED. So it allows you to connect a single circuit between two other circuits. And that's the same chart we showed before for the different types of switches. So what is the function of a single pole double throw switch? Got a guess?
C.
Sounds good. Okay, relays. A relay is just a electrically controlled switch, which allows you to remotely control it. That's its main purpose. So you can have a switch somewhere a long distance away and operate. The switch may be up on top of a tower or something like that, or to control a access gate outside the property or something. What is a relay?
A. Electrically controlled switch.
Right. Okay, meters are some of the other components, and they're used to display some quantity, normally as a numeric value. In some cases, it might be an analog or a digital representation. Typically, you'll see it to show the output voltage on a power supply, or on a transmitter, it may be showing grid current or output power. They're even used as time displays, frequency displays on your radio. There's some typical of the old analog type meters. You don't see them nearly as much anymore. You may still see them on a power supply. Some of the more modern digital meters, which are much more common. Which of the following displays an electrical quantity as a numeric value?
C. Meter.
A D or C?
C. Kevin, I don't.
try to use the phonetic alphabet because you'll need to learn it. So you might as well practice.
Charlie,
That Alpha, Bravo, Charlie, Delta.
Robert, can you see the chat?
What?
Can you see the chat?
No. Oh, 20 chats? My goodness.
Oh, no, it's just that, Kevin, you've been entering the answers in chat is all.
Oh. Okay. Because he's got kids in the background.
Gotcha.
All right. Oh, I wasn't aware of that. I'm getting old. I don't pay attention to everything. But I'm not as bad as some people. Integrated circuits. It's just a way of combining a lot of semiconductors together on a single, what we call substrate. It's usually a piece of silicon, and they, in the manufacturing process, can create transistors and diodes basically embedded in that substrate. And in the case of like a microprocessor, you'll have millions of them on that single little piece of silicon. They don't have to be digital like transistors and diodes per se, making up shift registers and counters and things like that. They can have analog functions, can be analog to digital converters, digital to analog converters, voltage regulators, which you'll see in power supplies to control a voltage. Oh, I knew it. It stopped working. It always does it. Here's a picture of one of the little ones with the cover ripped off. And you actually see that silicon substrate in there. And these are actually gold wires that connect from points on the substrate out to the pins on the actual package. And you can kind of see those little squares and things are all separate little components. Could be an array of transistors making up a section of memory, or it's all sorts of things. We talked about voltage regulators, which is an analog type of integrated circuit. Typically, they handle a little bit of power, so they may be in this kind of TO 220 package, which will handle a few watts. They may be smaller if they're lower power. This kind of shows a typical circuit of what's inside, and it will usually have a field effect transistor being controlled by a comparator, which is comparing the output voltage back to a voltage reference. Typically, that voltage reference circuit there would be one of your Zener diodes and a resistor. So if this was, say, a 12-volt regulator, that would be like a 12-volt Zener, and you'd be comparing the output to that 12 volts in this comparator. So whenever the output was lower, okay, you're going to increase the current flow and increase the voltage. So it's kind of acting like a variable resistor in this case. What is the name of a device that combines several semiconductors and other components into a single package?
Charlie, integrated circuit.
What type of circuit controls the amount of voltage from a power supply?
Alpha regulator.
Right.
Kevin got it before me.
Okay, we have fuses, and they're there to protect the circuit. So in the case of a current overload, the fuse will open up. Kind of like a circuit breaker, except the circuit breaker is resettable. The fuse, when it opens up, the actual element in there melts or fuses. So you have to replace it, like Dan had to do on his solar panels. But its main purpose is to protect other devices from current overload, which could create a fire. If you didn't have the fuse there and you were getting a tremendous amount of current, you'd heat something up to the point where it catches on fire, melts, or something. Picture of typical fuses. You see them in all kinds of shapes and sizes. These blade fuses are typically what you see in an automobile nowadays. The kind of cartridge fuses, the small bus type, you see in a lot of equipment. You can even see. Oh, you can even have them kind of like a surface mount, although it's very low resistance, and they will open up with a certain amount of current. There's polyfuses, which actually I believe reset themselves. I haven't used one in decades.
Those fuses right there, you've got them marked as cartridge fuses right there. That one on the left is red, so when you're looking at it in a circuit, it looks like it should be an LED.
Oh,
And that's what's on the power supply board in my Dell One computer.
okay.
All 3 times that I've repaired that power supply, that's one of the items that went, that and a couple of capacitors. I gave up on that. They took the power supply and they said, hey, let's see how much stuff we can bolt to the outside of this. So you had to do like a 95% assembly to get to the power supply and repair it.
Well, you still got these things showing up. I don't know what that's from.
Yeah,
Okay, what electrical component is used to protect other circuit components from current overloads?
Alpha fuse.
Good. Shielded cables. The purpose for that is to prevent coupling of unwanted signals or generation of unwanted signals. When you run wires through a shield, like is shown there, that foil, and there's actually a wire that runs through it that makes contact with the foil because you can't solder to aluminum foil, so it's just a contact type of thing. It causes that outer shield to act as a Faraday cage. Was something invented by or discovered by Michael Faraday. So that's why it gets the name. So if you have a conductive, this is a metal wall, if it's a conductive enclosure and you apply an electric field, what happens is it forces the free electrons over to, in this case, it's in this direction, so to this side, over to the left. And it leaves just a positive charge on the right side. So it's projecting an electric field out of it. It's kind of absorbing the electric field into it. So the effect is there's no electric field inside of it. So that's why if you put your cell phone, for instance, in a Faraday bag, which is a conductive bag, it's not supposed to be able to work. Actually, I think they still do.
Yeah, I think frequency.
I know they do in microwaves.
You might be able to put it into 2 bags,
Yeah,
block it out a little bit.
but
There is a heavier bag, yeah,
Yeah.
it's much more efficient. It's kind of expensive too.
But the principle of a Faraday cage is as long as the it may have holes in it or penetrations, as long as they are smaller than the wavelength of the wave you're trying to block, it won't go inside the cage. Your car acts as a Faraday cage, which is why your handy-talkie won't work well inside of a metal chassis car. You kind of have to hold it close to the window or have an external antenna. Which of the following is a reason to use shielded wire?
Charlie, to prevent coupling of unwanted signals.
Okay, so we learned about resonant circuits, probably more than you wanted to know, but you'll need to know it later. Different kind of switches, what they do, what a relay is, meters, integrated circuits, voltage regulators, fuses, and shielded cables.